Hello everybody! Alright, in this video we have talked about series and as far as their convergence and divergence, but we are going to start talking about power series, which will then lead us into Taylor and Maclaurin polynomials. Now, power series is essentially an infinite series that is defined in terms of x to a power. So notice I have x to a power, x to a power, some sort of x to a power, and an x to a power, right? And we have done ones that are, sorry, I should have had this ready to go, but we did ones on your quizzes and things. Let's see. For what values will this converge? And we have already done things like this is one of your quizzes. This is the answer to one of your quizzes. So if you're watching this video ahead of time, congratulations! You probably have an answer to your quiz. But we talked about an interval of convergence. So for values of x, as long as x is between -3 and 3, this polynomial will give me a very good approximation of what I'm looking for. We'll be able to write e to the x as a power series, sine of x as a power series, transcendental functions essentially as a power series. This is what that will help us do. Okay, I don't care. Congratulations, you didn't do it. So, in these types of questions, you may be asked to determine the center, the radius, and the interval of convergence. So the interval of convergence is just like our geometric stuff, except this first one that we have is not geometric because of this n+1 right there. So no longer can I use kind of the fact that the absolute value of the rate has to be less than 1. Usually in class I will do a warm-up using the ratio test, but the ratio test, if you remember, I said is very important, because I always do the limit as n approaches infinity of the subsequent term over the initial term, and if it is less than 1, then I converge. If it is equal to 1, then it is inconclusive. And if it is greater than 1, then I diverge, right? So that is true. The nice thing about this is if I converge when the absolute value of this limit is less than 1, this can work for any series. Any of our power series can be geometric, but it doesn't have to be. So this ratio test is all powerful. And essentially, if we can show that this is true, then for those values of x, I will converge. Now, an issue with this is that when I am equal to 1, I am inconclusive. So whatever I found my interval of convergence to be, I will need to check my endpoints. But I'll show you that when we get there. So what we are going to do with this, to determine the interval of convergence first, I'll talk about that first, and then I'll come back for the center and the radius. But for the interval of convergence, I'm going to take the limit as n approaches infinity of a sub n+1 over a sub n, and my goal is to have this be less than 1. Now in this instance, I'm not going to worry about writing my alternating part. You won't lose points if you don't write it because the absolute value will take care of that. So I will write, what, n+2 x to the n+1 over n+1 x to the n, absolute value less than 1. And with these things, do remember too that our interval of convergence, these x's, these are going to be values. Eventually, like if I have it from -1 to 1 or whatever, I have x values from -1 to 1. So we can treat these x's like numbers eventually. So I'll be able to factor them out of my limit. But let's go ahead and simplify. Let's practice our simplifying a little bit. So I have, let's see, the limit as n approaches infinity. Really the only thing that is going to happen is my x to the n's will divide out. So I have x times n+2 over n+1 less than 1. So like I said, the x here is just some number. It is going to act as some number. So I can go ahead and factor it out. So absolute value of x times the limit as n approaches infinity of n+2 over n+1, and I want it to be less than 1. Good Lord. Right? So that limit is going to go to 1. So really what I have is the absolute value of x times 1 needs to be less than or equal to 1, or less than 1. So in order to take care of this, I can do -1, absolute value of x, and +1. So this is my interval of convergence. The thing here that we need to be careful of, like I said, is at 1, right? I found when I am less than 1, and it is less than 1 for these x values between -1 and 1, but it is exactly equal to 1 when x is -1 and x is 1, which is inconclusive for my ratio test, which stinks. But all that means for us is what we are going to have to do is check our endpoints. So when x equals -1 and when x equals 1. If you actually have to do this stuff on an AP test, this full problem would be almost a full problem on the AP test. ABC, probably part D would be different, but ABC. So for me, I'm just going to ask that you state whether it converges, diverges, and by what test. So let me show you what I mean. So if I'm going to put in x equals -1, and that is again into my x spot, so this will become the sum from n equals 0 to infinity of -1 to the n plus 1 times n plus 1 times -1 to the n. Now the -1 and the -1 to the n and -1 to the n plus 1, those can combine since they have the same basis, so I'll add the exponents. So this is equal to n equals 0 to infinity. Zoom in a little bit for you guys, sorry. So -1 to the 2n plus 1, n plus 1. And if I think about what this is going to do, this is not going to alternate, not at all. Because no matter what I put in for n, if I put in 0, it's going to come out 3. Or sorry, just 1. If I put in 1, it's going to come out 3. If I put in 2, it's going to come out 5. If I put in 3, it's going to come out 7, so on and so forth, right? So it's always going to be an odd exponent. So what I can say is that this is equal to -n plus 1, which I can show pretty easily diverges by the nth term test. So again, all I'm looking for in the last here that I was trying to explain is whether it diverges or converges and what test you're thinking about in order to do that. I'm not going to ask that you write all of the justification statements for all of these because that would be a tremendous amount of work. But technically on the AP test, if you have to do that, then you need to do that. And this would be not be enough for the AP test on this problem. Okay, and then we need to check x equals 1. So I'm going to throw 1 in for my x value, so n equals 0 to infinity of -1 to the n plus 1 times n plus 1, and then I would have 1 to the n, which really will not affect my function at all, not affect my sum, because it's just times 1, so that's kind of gone. So this is an alternating series, and I know that because I have an alternating portion that will alternate the signs there for sure. So I'm going to say this is divergent alternating series. That is enough for me in class right now. All right, so what that means is since both endpoints are divergent, my interval of convergence is -1 to 1. So now let's talk about my center. The center is just, what is the center number of those? So the center between -1 and 1 is 0. Look at that. The radius here is just how far I go out from the center in either direction. So the radius is 1. The center is something that you can tell directly from the initial. The center here is 0 because this x is just an x. The center on the next one is also just 0. Because the x is just x. So now when is it not 0? Well, this one right here. This center is c equals 2 because this x minus 2 represents a horizontal shift to the right 2 units. The radius is something that we're going to have to do a little bit of work to get. I'm not going to be able to get that just off of the graph. Sorry, not the graph. off of my sigma notation here, but the center is something that we can easily pick out. Okay, so that's really all that I'm going to be looking for on these types of problems. You will have to do a ratio test to determine your interval of convergence. You'll need to check your endpoints, the center you can get from the beginning, the radius you can tell based on how far in either direction your interval goes. All right, let's do another one. I'm going to skip down to part C next. I need to rewrite these notes, so if I've already rewritten these notes, this might be part A, because I will probably want to do this as part A. Stop it. Don't care. All right. So with this one, I've already determined my center, so I'm just going to go ahead and go into the ratio test. So I have x minus 2 to the n plus 1 over n plus 1, 2 to the n plus 1 times, I'm going to multiply by 1 over a sub n, which is multiplying by the reciprocal. And my goal here again is to be less than 1 by the ratio test. That doesn't look like a 1. That's a little bit better. 1! Okay. So let's divide out what we can divide out. So my 2 to the n is my 2 to the n, so that'll leave a 2 in the denominator since I have that first power. X minus 2 to the n and x minus 2 to the n, so I'll have an x minus 2 to the first. And the n's, the n plus 1, I have to leave there. I'm going to go ahead and factor out that x minus 2 as well. Just to make you see this limit a little bit more nicely. So I will have n over 2 times n plus 1, less than 1. So this limit here, my goodness. Try unlocking your screen, disconnecting your screen. I don't care. I don't want to back up, just lose everything. So this limit here, right, that's a rational function, that will go to 1/2. So I have, ooh, I goofed. That should still be absolute value, sorry. So I have x minus 2 times, this part is 1/2. So I have 1/2 absolute value of x minus 2 less than 1. You can multiply by the 2 first to get rid of the 1/2. And then I can rewrite this and add the 2. And also your radius is shown in this form of it. So our radius will be 2 in this case. But we'll be able to see after we do all this too. So add 2 to both sides. So I have 0, x, and 4. So I can tell that my radius will be 2. So center's 2, radius is r equals 2. And then I need to check my endpoints since they are inconclusive at 1. So I'm going to plug in 0 and 4, again in for the x spot. So for x equals 0, my sigma notation, 1 to infinity, negative 1 to the n plus 1, and then I would have negative 2 to the n over n times 2 to the n. Okay, so it looks kind of ugly right now, but I kind of want to do something with those 2 to the n's. So I remember my properties of exponents. That was an ugly sigma. You're ugly. No, you're ugly. Oh yeah? Oh yeah? I don't know. Right, I can split up the bases like that. And if you're like, whoa, 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 no you can't. You're pulling some magic crap. If I did 2 to the third times 3 to the third, that is the same thing as 6 to the third because 6 is 2 times 3 to the third. Stop it. Right, so that is all the same. So I can do that. What this means for me now is I can divide out my 2 to the n's. Those are gone. And my negative 1 to the n, these things, right, that'll become negative 1 to the 2n plus 1, which we saw is just an odd number. So this will always be negative 1 over n, which is a divergent p-series. Officially, it is my divergent harmonic series if I factor out that negative 1. So 0 is divergent. We need to check the other endpoint. So x equals 4 will give me negative 1 to the n plus 1, 2 to the n, since it was x minus 2 to the n over here, right? So 4 minus 2 is 2, all divided by n times 2 to the n. And in this case, there's no rewriting or anything I have to do that's fancy, but I can divide out the 2 to the n's. So this becomes negative 1 to the n plus 1 over n, which is a convergent alternating series. So what that means for us, since 0 diverges and 4 converges, my interval of convergence is 0 to positive 4, where 4 is inclusive. Alrighty. Stop it. Stop talking to me, messaging me. No! All right, I'm going to go back for part B here. So I'm going to go ahead and set up my ratio test. So now check out here. Remember, I'm substituting in n plus 1, so that's going to turn into 2n plus 2 factorial when I distribute the 2 in front. And then flipping it will be 2n factorial, 3x to the n, and I want this to be less than 1. So let's simplify. So I have 3x in the numerator, and that 2n factorial over 2n plus 2 will turn into 2n plus 2 times 2n plus 1, and I need this to be less than 1. Well, the cool thing here is if I factor out 3x, right? Again, you don't have to write this factoring out every time. I usually will not. I will just think about what is the limit. But you can if it helps you. This is no big problem. Right, because that limit, that will go to 0. So since that goes to 0, the absolute value of 3x times 0 will always be 0. So 0 is indeed less than 1. So no matter what value I put in for x, it will go on forever in both directions, but still I'm putting a number in for x. I'm not putting in infinity, so it's not indeterminate. But since it goes on forever, the interval of convergence is negative infinity to infinity. Those are not real endpoints, so I have nothing to check. This is nice. So this is my interval of convergence. My center we already determined is c equals 0, and my radius is indeed r equals infinity, believe it or not. Probably depending on what book you read, it may change that, but for our purposes, I believe I've seen AP Classroom write it as that, and I believe I see our textbook write it as that as well. Okay. Also, at bare minimum, the center converges. At bare minimum. So here, my center is c equals 0. So let's do our ratio test. You're killing me, iPad. Stop it. Right, and I will be able to factor out an x. What is that? That's an infinity. And this will end up as n plus 1. All right, so the deal about this one, this part goes to infinity. So since that goes to infinity, I have absolute value of x times infinity is less than 1. So really the only thing for this to work is not going to work. This will be indeterminate if I had x equals 0. But the center is c equals 0. So my interval of convergence is only the center, which is x equals 0. That is it. That is the only thing that will work. If you try anything else, no. They will all diverge. All right, my center, as we already determined, is 0. Stop trying to back up. Have you not figured it out by now? My radius will actually be r equals 0 as well. It can have a 0 radius. Okay. iPad, you're killing me. I'm just going to unplug you and hope you still connect to AirPlay. All right. So the next thing, with these, it is useful in courses like abstract algebra and beyond, different things. But we need to be able to take the derivative or the integral of power series. So notice, please, I'm only doing them in terms of x. So the only thing that is changing is the things around the x. Right? That is the part that is going to be changing from the original series. So essentially, I'm going to be using, if I want to take the derivative, the power rule where I bring the n down to the front and I take 1 from the exponent. If I do the antiderivative, I add 1 to the exponent and divide by the new exponent. All right, so that's all we're going to be doing here. Do notice that the index changed. If you don't change the index, I think you're still fine. So I usually leave the index alone. But this is the definition that I copied from the book. Okay, so let's see. Find f prime. Well, f prime, based on this, I'm going to leave everything else alone. So negative 1 to the n plus 1, that's not x. So the only thing I'm going to be messing with here is this. So I will bring down the n, so n times x minus 2 to the n minus 1. All of that divided by n, since there was a divided by n in my original. And do note too, if this was like a 3x minus 2 or something like that, I would have to do the chain rule and multiply by a 3 out there as well. But it's not, so I'm not going to worry about that. Okay, the n's will divide out, so I can rewrite this series as n equals 1 to infinity of negative 1 to the n plus 1 times x minus 2 to the n minus 1. All right, and then it asks for double prime, so I'm going to do the derivative of that. So I get to do it again. N equals 1 to infinity. So I'll bring down the n minus 1 now. Times x minus 2 to the n minus 2. All right, the integral. So I'm going to add 1 to the exponent. Again, this is of my original. So it will become n plus 1. So the integral of f of x dx equals sigma n equals 1. Keep your index the same. To infinity of negative 1 to the n plus 1 times x minus 2 to the n plus 1. All of that over n times n plus 1. Alrighty, that was it. That's it. That's all of 9.8. Yep. And then we'll come back and get 9.7. So the big deal about this is that really all you're doing for the interval of convergence is doing the ratio test for when you are less than 1 and check your endpoints. All right, hopefully this was helpful. Enjoy, you big disappearing monkey. He's going to go away. Bye, little monkey. I will see you all soon.